Okay, so we're going to be looking at this example here. So we've got this upward force of 30 kilonewtons applied that is being restrained by these three cables. So first things first, what we want to do, draw a free body diagram of the system in question. So we got this nice diagram here. What I want to do is kind of replace that with a set of two different free body diagrams. So the first one that we're going to be doing is kind of looking at it kind of straight on along the axis of AD there. So kind of looking down the x-axis. So if we have our point D, the first, and then we define our axes here. So that'll be the Z direction, and this will be the Y direction, kind of based upon the coordinate system outlined in that chart there. So first things first, at D, we've got the force applied. So that is a force that is straight upwards, so in the positive Y direction, and that is 30 kilonewtons. And then we have two other forces that we would see on this chart, in this free body diagram as well. So we've got the line from D to B, call it FDB, and we've got the line, the cable from D to C. So we'll call that FDC. Now, what we could do is we could kind of figure out what that angle is and throw in some cosines and sines or what have you. And, you know, that wouldn't be terrible, but I think generally speaking, when you're dealing with 3D problems, it's easier to kind of exclusively work with your unit vector annotations. And one thing, if anyone's wondering, the cable from A to D, that's not showing up on this free body diagram because it's acting in and out of the plane that we're looking at. So let's just go ahead and, well, let's draw the second free body diagram while we're at it, in order to allow us to figure out, you know, get a better idea of what we're looking at here. So we've also got, kind of looking at it, let's say top down. If we're looking at it top down, if we start at D, and based upon kind of the looking at it top down, we've got this cable from A to D. And then looking at it top down, we still got FDC and FDB. Those both still show up on this diagram. And then the vertical force here doesn't show up on this diagram because it's coming out of the page. So again, looking at that top down, so based upon the coordinate systems specified, that one is a positive in the x-axis, and this will be a positive in the z-axis. And yeah, we could also do the XY plane, but yeah, that isn't quite as useful because it kind of doesn't reduce any of our terms down to 0. So let's kind of ignore that for now. So anyways, like I said, we generally want to be working with unit vectors here. So first things first, we can go ahead and just figure out those are. So essentially, the easiest of these is going to be the unit vector for not AD, D to A, because that one only has any displacement in the along the x-axis. So that essentially we know that that is going to be we're only going to have an I term there, and because the displacement from A to D is along the x-axis but away from the origin, that's going to be a negative I. And then our J and K terms, those are 0. As for the other two, again, we actually have to do a bit of math for that one. So if we want to do D to B, first step there is going to be basically to define that distance. Distance for dB, that's just going to be the square root of the total offsets from D to B. So based upon the dimensions given, that'll be the square root of 1 squared plus 0.75 squared plus 3 squared. I guess I'll write that down. 1 squared plus 0.75 squared plus 3 squared. These are all in meters, so I'll just take the square root. It ends up being a meter, so I'll just stick the meter term outside for the heck of it. And that ends up being 3.25 meters. So then we define our unit vector from D to B in terms of the displacement in x, or dB, divided by the distance, the total distance from D to B, times I, plus displacement in y, dB over the distance dB plus j, and then also our displacement in z, dB over the distance from D to B times K. So that's simple enough to find out, right? So we've got our values here. So the displacement in the x direction from D to B is 0.75. So 0.75 divided by 3.25, that's going to be 0.231 I. And then the displacement in the y direction from D to B, that's going to be -3. You're going downwards. You're starting at the origin, or you're starting at an elevated point and you're going downwards. So you do need to keep your signs in mind. I'm actually going to go ahead and erase that plus sign there and replace it with a negative. instead of adding a negative. So that's minus 3 divided by 3.25. So minus 0.923 J. And then we also have the K term. So the K is based upon the z-axis displacement. So for D to B, keeping in mind that here we got our things here. The z-axis was defined in this direction. So when we go this way, that's actually negative for the D to B displacement. So that'll be, come on, need my pen. That'll be negative and negative 1 over 3.25. That'll be negative 0.308 K. And so we just go ahead and that gives us, that's our unit vector for dB. That basically allows us to kind of figure out what the force components are based upon the individual force components are relative to the overall tension in that particular cable. So we just do something similar for our D for our D to C. So the distance from D to C, it's just going to be square root of let's see, starting with x 1 squared plus 1.5 squared plus 3 squared, and again this is all in meters. One plus 1.5 squared plus 3 squared. It's 3.5 meters. So same idea for figuring out our unit vector. That's DC going to be equal to, I'll just go ahead, so 1 over 3.5 I, again meters over meters cancels out, plus for the y component, again negative 3 over 3.5, and then this time for our z component, the displacement is in this direction. That's in the positive z direction. So that'll be 1.5 over 3.5. Oh, sorry, I forgot to put the j for here, and then k. So numbers for that: 0.286 I minus 0.857 J plus 0.29 K. Okay, so now where do we go from there? So one thing that we're going to need to do is essentially we're going to need to basically figure out kind of the first step in balancing these equations here is going to have to be figuring out how big these are relative to one another. So the easiest way to do that, we know that there are only two forces that are acting in the z direction. you got our FDC and our FDB. So we can just take the sum of the forces in this in the z direction and have that equal to 0. This thing's in equilibrium, so those need to be equal to 0. So in order to do that, essentially, we just add up those two things. So when we want to take the sum of the forces in the z direction, what we do is we just take this force and multiply it by the k component of its unit vector, and then this force, and this FDB, multiply it by the k component of its unit vector, then take FDC and multiply it by the k component of its unit vector, and those two things should add up. So we'll just go ahead and do that. So FDB times negative 0.308 k plus 0.429 k. I guess I wrote that a bit too large, times FCD. So we can just equate those. So if we add the FDB term to the other side and then divide out, we just get FDB is going to be equal to FCD times 0.429k divided by 0.308k. So our unit vectors there cancel out, and 0.429 divided by 0.308, that's going to give us FDB is going to be equal to 1.39. Let's go to 4 significant digits for that one because it starts with a 1. 3 times FCD. Okay, so we don't know what those are yet, but we know the ratio between the two. Well, next thing's next. What's the other direction that we can start figuring out the relationships for? Well, if we know what the upward force in the y direction is, then we can basically use that to solve for both FDC and FDB. So by taking the sum of the forces in the y direction, equating that to 0, we can solve for these two forces. So we do that by just adding up the forces that are acting on our point D here. So the y components of that force. So we got the straight upward one, the 30 kilonewtons. And then we've also got the y components of FDB and FCD. So we find those just by taking FDB and multiplying it by its j value, but by the j component of its unit vector, and do the same for FDC, multiply it by the j component of its unit vector. Okay, so I know both of those are negative values, so I'll just go ahead and throw a negative there. So let's start with FDB. So negative 0.923 times FDB and minus 0.857. FDC. Oh, sorry, FCD. Wait, no, DC. I was right the first time. DC. We're acting from the point down to the ground. All right, so we've got those, but we can take this value here and plug it into here as well, in order to essentially leave us with just the one unknown. So let's take these two terms, add them to the other side of the equation. So that'll give us 0.923 times 1.393 FCD. Oh, that's where I went wrong. FDC. Had it written wrong here. Sorry about that. Is there anywhere else I did that? Yes, here as well. These are all supposed to be DCs, not CDs. Oh wow, I did that a lot. Alright, that's all of them. Okay. So that term there with plugging, got that term there, except plugging in this value for the FDB. And then minus another plus another 0.857 FDC, because we had added both to the other side of the term, is equal to 30 kilonewtons. So again, we can just solve for our FDC there fairly simply. FDC is going to be equal to 30 kilonewtons divided by 0.923 times 1.393 plus 0.857. So 0.923 times 1.393, that's and then plus another 0.857. So that bottom term there is equal to 2.14, which gives us an FDC of 14 kilonewtons. So based upon that, we can just go and solve for our FDB as well. So we take the 14 kilonewtons and multiply it by 1.393. Which gives us 19.5 kilonewtons. Okay, so well, we're almost at the home stretch here. So we've solved for of the components that we're looking for. We've solved for all but one of them. The only one we're missing is this F. Oh, I screwed up that one too. My apologies. That one should be FDA, not AD. My apologies. So, yeah. Anyways, we've got our we've got all the unknowns except for that one. So the way we do that is take the sum of the forces about in the direction we haven't yet. So the only one we're missing out on is the sum of the forces in the x direction. So that one is just going to be our forces here times the I component of their unit vectors. So we'll start off with FDA times negative I. It's just its unit vector is just a -1 in the I direction. So FDA times -1, and then FDB times, let's see, what's the unit vector? 0.231i. And then we've got our FDC times its unit vector in the I direction, which is 0.286. And all that needs to be equal to 0. So simple enough. So we can just, we got a negative FDA here, so we'll just add that, add FDA, add one FDA to each side in order to move this sucker over here. And that is going to be, we can also plug in our values for FDB and FDC here. So 19.5 kilonewtons times 0.231 plus 14 kilonewtons times 0.286. So 19.5 times 0.231 plus 14 times 0.286. That is going to be 8.5 kilonewtons. So that's that. We've now determined the tension in each cable. Like I said, generally speaking, I find that the unit vector approach is the most straightforward. It's the one that is least likely to have you run into issues figuring out kind of what angles. You don't need to worry about whether or not the angle that you're trying to take a cosine for or sine for is relative to an axis when measured on a here. Let me see what I'm trying to say. So say we've got x, y, z, and we've got and say we've got kind of this point in space here, and we're obviously worried about this unit vector, this force here. If we start worrying about sines or cosines and so on and so forth of that, then you start getting into worries about whether or not the angle that you're trying to take the cosine of is actually, say, this angle here, or whether or not you accidentally screwed up and instead took the angle of the projection of this vector onto this plane and then took that angle there. It can often be hard to visualize, to see whether or not you're actually looking at the right angles. So unit vectors really does allow you to kind of skip a lot of that. So you're always sure that you're kind of working with the right values. As long as you keep your sign conventions in mind. If the displacement from, say, D to B in the y direction is negative because we defined the y-axis is up, your unit vector needs to keep that in mind. But as long as you do that, it's fairly straightforward. It's kind of hard to screw up. And that's about it.